Hello my esteemed viewers, in this tutorial we will clearly explain the various stress levels that are reached by the material whenever the component which is made out of a particular material is subjected to axial load which is gradually increasing. Whenever materials like mild steel, high strength steel, high carbon steel, copper, wrought iron, cast iron, tungsten and aluminium is subjected to the axially increasing load, they will reach their level, various levels of stresses, that is various levels of resistances built up in them depending upon the material. Here the point of concern is as to what is the magnitude of the stress level that is going to be reached by the material. Of course, the magnitude depends upon the material itself. We need to test in order to verify in order to measure the levels of stresses in terms of their magnitude. We need to test the material, the object made out of a particular material under gradually increasing axial loads under certain test standards. The test standards are the material should be made into some kind of a form like this with some kind of a shape like this, and this should be subjected to a gradually increasing axial load, and this shape will have grip lens, and these lens will be put into the jaws of the machine, that is typically universal testing machine, and it provides a grip to hold the specimen in place. And this is the central portion is called as gauge length, where the strain is gauged, the strain is measured. And this is the typical UTM machine, and here is the specimen which is placed, and this particular portion will make a downward movement, and this particular portion will be standstill, thereby the load is applied, thereby stress is generated. And this particular tutorial comes with a terminology alert. There are many terms that are to be remembered, that are to be fundamentally understood as far as our further go in this particular excellent subject is concerned, and we need to understand certain fundamental terminologies about stress levels. The first stress level is working stress level. Working stress level is also variously called as allowable stress, permissible stress and safe working stress. By definition wise, it is the stress level at which material can work safely. Material can bear load safely. Therefore, the components will always be designed in such a way that it will develop safe stress. This stress cannot be determined precisely in a laboratory. It could be a dam should function safely, a building, multi-story building should function safely, so also the components of a machine should behave safely, and also a boiler, a pressure vessel should also work under safe stress level. What is the amount of safe stress level? The safe stress level is in the material itself. Yield stress, the next higher level of as the load gradually increases from a level which has caused the working stress level to an increased level, it may turn into yielding of the material. It is a constant stress at which material flows like a plastic. You will see deformation which can be seen with naked eye. Particularly in case of ductile materials, there will be large deformation at this level of stress. For example, mild steel will reach up to 240 MPa, 240 Newton per millimeter square when it reaches yield. By that point of time, it will have shown a large elongation which can be observed. High strength steel will go up to 550 Newton per millimeter square. And this is yielding of a rod in tension. It will form a typical neck neck formation which can be seen, and this is the yielding of a beam in bending. You can see a sudden flow of this beam, and it has taken a different shape altogether from its straight shape. The yield stress and its effects can hardly be noticed in brittle materials. Of course, ductile materials will showcase the yield in a typical way, so that it can be seen. As far as brittle materials like wrought iron and cast iron are concerned, and concrete is concerned, it will never show a marked behavior, something like this, and it will break suddenly, or it may show off wide cracks. And this is a cast iron component, and you can see some kind of a local failure, and and it doesn't give warrant, it doesn't give a notice, while ductile material will give a warrant of an imminent failure. Ultimate stress is the maximum stress, greatest stress a material can withstand without failure, or just before failure, or just before rupture. This stress will never be used for design of components, understandably, without saying, for the sake of safety. This stress level can be determined in a laboratory state. Yield stress in case of ductile materials, and ultimate stress in case of brittle materials can be determined sufficiently accurately in laboratory tests, while the working stress cannot be determined accurately. And at the ultimate stress level, after the happening of the ultimate stress level, the specimen will be into pieces. And if we make a sketch of this behavior in the form of a stress strain diagram, stress going along vertical axis and strain going along horizontal axis, the first stage, there will be uniform extension, there will be uniform stress, and stress will be proportional to strain. There will be uniform stress, and there is no noticeable elongation, and this is the elastic range, and this point is elastic point. And upon increasing the load, it will reach proportionality limit, and the stress will never be proportional to strain, and it will reach yield point. At the time of crossing proportionality limit, we will notice what is called as, this is a microscopic view of the specimen, of course, and we will see some kind of a diffused necking. Necking has already started, but it cannot be noticeable. And when it crosses the yield, the material, see, it's a constant stress. Yield is defined as a constant stress. It doesn't require the increase in the stress, and there will be too much of strain. And if you project this point and this point, you can notice some kind of a plateau, and the stress is constant, and at this particular point of time, particularly in ductile materials, I hasten to add this, and you will notice a large deformation, and this point is called as yield point, and the corresponding stress is called as yield stress. And here you will see a noticeable, a local kind of necking, look at a weak point. Of course, at this particular point, if we once again progress in the increase in the load, there will be some kind of a crystallographic arrangements within the metallurgical arrangements within the material body, within the heart of the material, and it will pick up the strength yet again, and this is called as strain hardening. So due to this picking up of the strength, there will be increase in the stress, level, and it will reach a peak. At this particular point in time or point in load, there will be a localized neck formation or weight formation, and there is a drastic reduction in the diameter. Therefore, it doesn't take too much of a load to break the specimen, and the load falls down, and the specimen will be into two pieces. And you can see over here, and here also you can notice the fracture, and this is the failure stage. And this particular curve has reached the breaking point, and if you project this along y-axis, you will get breaking stress, and here if you project along y-axis, you will get ultimate stress. Therefore, ultimate stress is the peak stress before failure. This we need to understand. And at this particular point of time, there will be local necking, local necking. There is a drastic reduction in the diameter, so it doesn't take too much of a load to break this particular specimen. Therefore, stress will fall down. This is uniform deformation, this is diffuse necking, this is localized necking, and this is the fracture. And this is the chronological order of the stress reaching a particular the various levels and the corresponding effect in terms of necking, diffuse necking, localized necking, and fracture. So any member or any structural component as a matter of fact cannot be designed for yield stress or cannot be designed for ultimate stress. We need to design things only for working stress. So in this context, a number is defined. This number is called as factor of safety. It is the ratio of ultimate stress to working stress or yield stress to working stress in case of ductile materials. The determination of factor of safety for the design of a particular structure is a matter of expertise and experience of the engineer, for the simple fact that working stress cannot be found out in a laboratory typical experiment. Therefore, we need to decide this factor of safety. However, traditionally, factor of safety is defined as a ratio of ultimate stress by working stress as far as brittle materials are concerned, as far as ductile materials are concerned. Since they can show off their yield stress, factor of safety is defined as yield stress divided by working stress. And anyway, deciding on a factor of safety value depends on several parameters. It is instead, as a design engineer, will compute the working stress by deciding the factor of safety. So what we need to do is we have to divide ultimate stress by factor of safety in order to take out working stress, or we need to divide yield stress by factor of safety in order to arrive at working stress, particularly in case of ductile materials. However, the factor of safety, deciding on factor of safety, calls for the expertise or experiential observation of an engineer. The value of factor of safety is decided by the engineer, as I told. It depends upon the value of factor of safety depends upon degree of safety required. For example, a dam will have higher factor of safety, so also high story building, okay, and so also a machine component taking huge amount of stress, maybe a shaft, because the failure of a dam would incur men and material loss. And the failure of a high-rise building will also incur huge loss of leaves. And so also the breakage of a specimen, breakage of a shaft in a typical automobile will also involve in huge human loss. Therefore, whenever human loss and material loss is expected upon failure of a particular component, high degree of factor of safety is required. When you decide upon high degree of factor of safety, the working stress will also reduce, because it is yield stress divided by factor of safety or ultimate stress divided by factor of safety. So that will reduce the working stress, and reduction in working stress can only be obtained by increasing the area. Therefore, by increasing the factor of safety, we will also increase the area of cross section. We will make the components or a structure robust. The degree of economy, and for a temporary structure like this, a temporary structure and a simple machine, and for a residential building, the factor of safety will be low. And dependability of the material also matters, because a ductile material, if a component is made out of ductile material, it will show off during the failure. Therefore, it can have a relatively lower value of factor of safety when compared to brittle materials like concrete, which will never give a warrant before its failure. Therefore, brittle materials, components made out of brittle materials, will be designed with a higher factor of safety when compared to components involving ductile materials. The nature of the structure, that means whether a structure or a component is temporary or permanent. The type of loads, is it a static load or is it a dynamic load? Because dynamic load will impart extra load and it comes dynamically. Therefore, the impact impact induced by the dynamic loads is much more than the static load. Therefore, any component or any structure which has to sustain dynamic loads will have to be designed for a higher factor of safety when compared to a structure which will be taking static load. The factor of safety anyway, nevertheless, factor of safety varies between 2 to 5. A maximum of 5, minimum of 2. So this brings us to a concept of what is called as elasticity and elastic limit, because we need to design the structures or components within their elastic limits. Elasticity is a property of a material by virtue of which the material will regain its shape and size after the removal of the load, like an elastic material. This elastic property of mild steel, high strength steel, aluminium, copper has been meticulously used in developing springs and developing materials or components which can bend and which can regain its shape. And you have seen the rubber band, when you release the load, it will go back to its original position. Elastic limit is the stress level up to which the material behaves elastic. And as I told earlier, if you plot stress and strain, it will have a linear relationship. Any material on earth will have a linear relationship. The matter of concern is what is the value of the stress at the elastic limit. Usually the elastic materials like mild steel and high strength steel will have a higher elastic limit when compared to rubber band or when compared to a plastic material. Therefore, it is rather logical to say rubber band or the components made out of rubber are less elastic when compared to components made in steel. And there comes along with a Hooke's law, provided by the famous scientist and engineer Hooke. And it is coming to be called as law of elasticity, and he is the person who postulated this particular law. Within elastic limits, stress and strain is linearly related. That is, stress is proportional to strain. So if we formalize his postulation or his proposition, stress is proportional to strain. So if you remove this proportionality constant, we are going to induct E sigma equal to E into epsilon. Therefore, E equal to sigma by epsilon. Sigma is known to us, strain is known to us, and this comes to be elastic modulus. Modulus means measure. Therefore, elastic modulus is a measure of elasticity. That is, if modulus of elasticity is more, the material will be more elastic. If it is less, it will be less elastic. And since this is stress expressed in Newton per millimeter square, strain is a unitless parameter. Therefore, even modulus of elasticity will also have the same units as that of stress. And this is modulus of elasticity. Thomas Young found that the modulus of elasticity is unique to every material after he conducted several experimentations. And later on, it was called as Young's modulus. Young's modulus in honor of his invention. And this Young's modulus varies from material to material. For example, rubber has 0.1 GPa modulus of elasticity, concrete has Young's modulus of 30 GPa, aluminium scales at 100 GPa, steel at 200 GPa, and diamond possesses highest elasticity or elastic limit or Young's modulus to the tune of 1220 GPa. And in the same token, we can extend Hooke's law to shear stress and shear strain relationship also. And there emerges like elastic modulus, rigidity modulus. Within elastic limits, even shear stress is also linear with shear strain. That is, shear stress is also proportional to shear strain. This is tau that we have accepted as a notation for shear stress. Shear stress is proportional to shear strain, that is gamma. And if you remove this proportionality constant, we will induct G, which is called as rigidity modulus. And if you want to define G, G will be equal to shear stress divided by shear strain. And I recall the attention of my esteemed viewers that shear stress and shear strain will have a different connotation, and you should recall your memory that I told shear strain will bring up a complete deformity in a structural component, a complete change in the configuration. The entire shape of the component will be changed if a component is subjected to excessive shear strain. And here comes a measure of shear taking capability, and this within elastic limit, of course, and this measure is called as rigidity modulus. How rigid? More the rigid the material is, more will be its rigidity modulus. For example, aluminum will have 25 GPa as its rigidity modulus, and steel at 80 GPa. Diamond, once again, it is 530 GPa. So with this, we will come to the close of this particular tutorial, wherein we discussed various terminologies and associated stresses and associated materials and associated effects. And till I come out with the next proficiently increasing complexity tutorial on solving the problems of using whatever that we learned hence till now. Until then, bye, and if you have liked this video, kindly subscribe to my